Okay, here we go, young people. We are going to be talking about the values of K and what that means. We've just learned that K is an equilibrium constant, okay, and is found by taking the product's concentration over the reactant's concentration, obviously using some stoichiometric relationships there to get all of that done. So what does it mean if K is equal to 1? If K is equal to 1, then we have an equal ratio of products and reactants, meaning neither one is favored. Both are likely to happen. Okay, if it's greater than 1, then K being greater than 1 means that the products are favored because you have a large number on the top and a smaller number on the bottom, meaning the products' concentrations are higher. If K is less than 1, that means the reactants' concentrations are higher. A smaller number on the top, larger number on the bottom gives you a K of less than 1, and that means the reactants are favored in the reaction. So we can see how that works, okay? So what changes K? Two things can change K. The first thing that can change K is temperature. K, or equilibrium, is temperature dependent. Anytime we change temperature, we change the equilibrium constant. So equilibrium constants are only good for a single temperature. They have to be calculated for each temperature change you make. The other thing that changes it is any change in the reactants, any change in the stoichiometric relationship you had. So if you do anything to the original reaction, it changes it. So whatever you do to the power of K. So for example, we have 2NO plus O2 gas in equilibrium with 2NO2, and we see that K is 4 times 10, or 4.6 times 10 to the 13th, meaning that the products are favored here. The products are favored because we have a K greater than 1. So what happens if we do something, if we change the coefficients? So what happens when we take NO gas and half everything? Well, that means we half K. What's the change? K prime, or the new K, is K to the 1/2. So 4.67 times 10 to the 13th to the half power gives me 6.83 times 10 to the 6th. So everything would be halved. Okay, so what if the reaction has changed? I'm sorry, we've already seen all of this. An example, there we go, reverse the reaction, so we flip it. Well, that means, what is the change? The change is K prime is 1 over K. So we do that. What's 1 over 4 times 10, 4.6 times 10 to the 13th? And we get this number. And look at how small that is. That's very, very small. So what's being favored? Well, the reactants are being favored in this case because we have a small K, and the reactants are the same thing as the products up here. So that makes complete and total sense. So I can also find it from a reaction mechanism. And this is very much like Hess's law. So this is what we have. What is the Kc? So the steps, here's the first step, and notice Kc for the first step. Here's the second step, notice Kc for the second step. Do we add up and get the original equation? And the answer is yes. Half of O2 cancels out. Okay, we have NO2, we have NO on this side, NO on that side. Okay, something's happening. We might have to flip some stuff around here, but we'll figure it out in just a second. Yeah, we're going to have to flip some stuff around. So here we go. To find Kc, Hess's law, the same process. Okay, so instead of adding, multiply K values. So here we go. That one didn't make very much sense, and I'll go over that in class tomorrow. All right, so what if we have pressure instead of molarity? Pressure instead of molarity is very similar. It's still an equilibrium. We still reach an equilibrium, but instead of having an equilibrium of concentration, we have an equilibrium of pressures, where we still are using the stoichiometric relationship. So if you see C here, we have little c here, and we have the pressure. So this is called Kp. You notice the change? Before we were using Kc, now we're using Kp. Kp means that it needs to be in pressure. If you see a Kp and you're given moles and you're given liters, you have to calculate pressure using the ideal gas law, okay? PV equals nRT. So all of those things are possible. So if it says Kp, you must use pressures. Given moles and liters, this is again what I was saying. You must use temperature, and PV equals nRT to get the pressure of each species. So Kc is molarity. Keq is either. Keq is a generic way of saying K, and so if you saw Keq, you would use whatever you were given. If you were given pressures, you'd find the Kp. If you were given molarities, you find the Kc. So all of that is included there. Okay, this will be ending our conversation about the introduction of equilibrium. So I look forward to talking a little bit more with you about it tomorrow. Thank you.